Welcome back, folks. Here's the last method that I'm going to introduce to find the Thevenin resistance of a fixed circuit. This one's nice in a lot of ways. It takes a little bit of work, but the limitations I think you're going to like. Okay, so I'm still abusing that same example. We're not done with it yet. I think we're going to have a few more videos on it. But we're all the way at the bottom. There it is. Same problem. We've found Thevenin. We've found our Thevenin two different ways. Here's our third method. Okay. And the limitation on this one is none. So if you're only going to learn one, this is the one that's always going to get you the answer. The problem is a lot of people don't know this method, and they don't even know the limitations of the other methods. So there is a lot of use in being able to communicate with other engineers. So if that's what they've learned and they're comfortable with, then you have to be able to talk to them and say, yeah, you're right, that's a great way to find our Thevenin, but you know, we have a dependent supply in the circuit, so we can't use that first method, equivalent resistances. Or when we have a dependent supply, but there are no independent supplies in the circuit, we can't really use method 2, so we're left with this one, which just flat out works. So I want you to be comfortable with all three of them. I argue with myself constantly over which one. If I was only going to teach you one, what would it be? I want you to be better than me and better prepared for sure. So I give you all three. You're smart enough to understand that there's three methods, there's limitations, you got to be careful where you use them. So let's do this one. Last one. Guess what our Thevenin's going to be? It's still going to be 7. Still going to be 7. Okay. No limitations. We're going to remove the load if drawn, like we have been doing. We're going to replace independent supplies with their ideal resistances. So a voltage supply is a short and a current supply is an open. Essentially, we have to turn off all the other power being supplied to the circuit. We're going to connect a new voltage supply to where the load was connected. And I'm going to call that V new, V sub new. And then we're going to find the current through that new voltage supply. And I'm going to call that I sub new. And we're going to use those to calculate our Thevenin. Okay? Now, the value of V new does not matter. I usually have the class pick a number. Random number. Doesn't matter. I'll work it with whatever number. Maybe I'll figure out how to get you a random number. I still don't have my Dungeons and Dragons dice. They're in my office. Nope, that's not it. They're in my office on campus. Still can't get to it. So maybe I'll just use a random number generator to make that happen. Okay, so I've already copied down the problem, and let's work through those steps. If you need to follow along in the image that I post with the video, which is what I'm drawing on right now, to look at the steps. I recopied it. We remove the load if it's drawn. In this case, it is drawn, so we're just going to disconnect that load. Okay. All of the other independent supplies, well, we only got one here, are replaced by their ideal resistances. It's a voltage supply, so this one's replaced by a short. So far, it looks like method 1, doesn't it? It really does. But we're going to take a little bit of a turn here, and we're going to put in a new supply that looks like this. Okay. And we're going to give it a value, V new, and I'll go figure out that value in a moment. And then we're going to find the current I new. And we're going to use those to calculate it. Give me a moment. I got to figure out this random number, and that's what we're going to use for V new. And here's my solution. So I can do it on screen and you believe me, right? 'Cause I wouldn't lie to you. I wouldn't lie to you. It's a random number. It'll work. So the way I'm going to generate this is using my TI-84 emulator. I have an actual TI-84 here too, but I want to do it on screen for you. So I'm going to say random integer between 2 and 10, steps of 1. I just don't want the numbers to get too crazy. If they did get crazy, it would still work. Okay, so look, 5, 10, 3, 9. I could use any of these. So we're going to use this one, the random integer 3. So I'm going to hook up a 3 volt supply right here. Okay, so let's say that's 3 volt. It's a random number. It doesn't matter what it is. If this changes proportionally, and our Thevenin is going to be consistent. So you can pick any number for that. Some people like to pick 1, some people like to pick 10, some people like to pick numbers all over the place. It doesn't matter as long as you do the analysis right and then ultimately the calculation for our Thevenin. So we have a value for V new. We got to go find the corresponding I new. Okay, so find it any way you want. I'm going to use the mesh shortcut. Okay, I think I have some room above my head here. So let's say, what does I1 touch? It touches a total of 9. What does it share with I2? It shares 6. Okay, what does I2 share with I1? It shares 6. What does it touch? It touches 11. I'm going to invert that, and I'm going to multiply it by, let's see, no voltage supplies on the first mesh, and then I'm dropping 3 volts on the second mesh as I move clockwise. Okay, that's going to give me I1 and I2. I'm running out of real estate here, so forgive me if I don't write out the vector of unknowns. I got I1 followed by I2, 9, -6, 0, -6, 11, and -3. Every time I work this problem, I get a different set of numbers here. Oh, they're not round by any means, but they'll work. So let's see, we've got -285.7 milliamps for I1 and -428.6 milliamps for I2. Okay, quick and easy. Think back to the beginning of the semester. How long would that have taken you? Crunching it all down to one resistor, crunching them all back up. Now you're fast and you're accurate. I love it. Okay, we find I new by saying, does I1 touch I new? Nope. Does I2? Yes, it does. Does it flow in the same or the opposite direction? It flows in the opposite direction, so we find that I new is equal to 428.6 milliamps. Okay, so we have V new. We picked that out of thin air, and then we calculated out where we did analysis to find I new. Now we have to calculate our Thevenin. Guess what it's going to be? 7. It's going to be 7. Okay, so our Thevenin, we calculate. Well, we got to follow Ohm's law again for this one, but this time it's whatever value we picked for that new voltage supply, and then whatever value of current is flowing through that new voltage supply. So 3 volts over 428.6 milliamps. I'm going to calculate it. I'm confident it's going to be 7, but I don't like to skip steps when I'm on video here. So 3 divided by that, it ends up being 7. Okay, 7 ohms, just like we did before. Just like we did before. Just the same result that we got before. Behind my head now. There it is. Okay, so this method is less known, but it just plain works. You can have circuits that have no independent supplies in them. You can still find the equivalent resistance. The other two methods, one of them works with test equipment. That's awesome, and a lot of people know it. And then the first method is the one that I think everybody's taught to begin with. So I think it's important for you to know that, just so that you can communicate with other engineers. Okay, so I think I've beaten this horse dead. Poor horse. What I would like to do now, and I'm going to do it in the next video, is use these values. So we got to make sure that this is actually an equivalent circuit, because that's the whole point of this. We want to find an equivalent circuit. So we're going to do that coming up now. Stay tuned and good luck.